Fantastic. I think we're going. Teresa, I think we're good. Thank you. All right, you're on. Thanks, Korkut.
Thank you. Thanks for the wonderful introduction. Yeah, I'm a chemical engineer. I have 3 degrees in chemical engineering. I somehow found myself in the world of transplantation. So I'll sort of take you through my adventures in the Wonderland. Typically, this is a treat for me too, because I don't get to speak to engineering PhD students very often. My typical audience these days is more surgeons and transplant surgeons. So as you'll see, the talk itself is more towards surgery, but I took a few asides to hopefully explain myself and how we taught as systems engineers getting into this world of machine perfusion and organ preservation. So let me start by appeasing the gods of disclosure that I have a number of patents, applications, couple of startup companies, and all that sort of jazz. In my defense as an engineer, this is sort of expected from me, but in the world of medicine, it's important to disclose these things. And if you have any concerns, I'm happy to discuss them further later on. So some of this may be old news to you, so I'll skip through this quickly, but I'm happy to answer more questions, of course. The transplantation is sort of a miracle cure. It's essentially spare parts for human beings, right? So if you look at, if you actually calculate how many people die, a lot of us, or most of us actually die because one of the vital organs stopped functioning. And there's a calculation by Greg Fahey that about 30% of all the deaths in the United States could actually be postponed significantly if we had spare parts for human beings. So this treatment is extremely effective. For most organs, the survival after 1 year of transplant is over 90%. So this sort of creates a dynamics from a technology limitation to supply limitation problem. In that we do need donor organs to transplant to people who need them. There are more than 100,000 people waiting for organs in the US, and if you talk with transplant surgeons, they will tell you the actual demand is 4 or 5 times that. It's just that people are not even put on the waiting list because they will never have any chance of getting one, so they don't want to give false hope. And this is the United States where the transplantation was developed. In most of the world, the situation is much more dire. The World Health Organization estimates less than 10% of the demand being met. There's an interesting part of this question, though. So you assume that we don't have enough organs because people are not donating their organs, and that's not necessarily the case. What's happening in reality is that we can only use a fraction of the organs that are donated. So, for instance, the majority of the organs we transplant come from a very limited number of patients, about 19,000 in the US if memory serves, who are donors after brain death, meaning the brain activity has ceased, but the organs themselves are functioning fine. And this occurs in a hospital in a controlled environment. So the organs can be procured without any major injury to the organ itself and be ready to go into another sick person and save them. But that's not the majority of the cases where people die and donate their organs. In most of our cases, we get hit by a bus or a truck or have a heart attack or something like that. And what happens in that case is the cardiac death occurs. These are called donors after cardiac death, DCD. But the problem in that case is because the heart has stopped, the organ is no longer being perfused with blood. There's no longer oxygen, nutrient supply. There's nothing taking away the byproducts of from the organ. And this is called warm ischemia, and it's deadly. For heart, there's about 15 minutes after which the heart becomes irreparably damaged. For the liver, which is my focus, it's 30 minutes. And other organs are similarly have a limit of in the order of minutes, before which you need to get in there, flush the organ with some cold storage solution so that this damage is less damaging, less severe. That being said, there is still a significant technology barrier to my engineering sensibilities anyway, in the way we preserve these organs. So what we do right now is we procure the organ, flush it with this University of Wisconsin solution at ice cold temperatures. put it in a box of ice, and literally run to the recipient hospital as fast as we can. Because we have in the order of hours. For the liver, the generally accepted limit is 12 hours of cold ischemia, and ideally you will have it less. Most hospitals operate under 9 hours actually. Because this is an organ that is actively dying. It is suffocating. It's suffocating slowly, but it is still suffocating because, again, there is no new nutrients, no new oxygen. So this limits us. It allows us to do transplantation the way we have been doing over the last 30, 40 years. But it is actively injuring an organ. So there are 3 consequences of that. One, the graft has to be in perfect condition to start off with, so it can actually take this cold ischemic injury, which is why we can use a DBD donors. The CD donors that are already warm ischemic, and then you put them on a box of ice, they rarely can take it. So that becomes a very significant limiting factor, which limits the number of organs available. Second, the storage limit is in the order of hours, which means we can only share organs regionally. So if the ideal donor for a patient in Minnesota is here in Boston, we probably can't send the organ there. There's just not enough time to do the procurement, send it there, and then the transplant surgeons in Minnesota to actually prepare the patient and do the operation. You have for the liver about 9 to 12 hours, as I mentioned. And in many cases, forget about it. It's just not possible. So we are limited to these basic, the statewide sharing. For instance, Minnesota has its own organ procurement organization. The neighboring states have their own, etc. And finally, because this is a cold stored organ, you can't really sense if this is a good organ or not. It's not really fully functional, so it's hard to assess. The consequence of that is that just by being conservative, we kind of throw away some of the good organs along with the bad just because we don't know. The way we decide if an organ is good enough is basically population statistics. If it's coming from an older donor, we basically say forget about it. Or if it's beyond a certain amount of ischemic time, we say let's not risk it. We don't necessarily look at the organ itself and say this is a good one or this is a bad one. So the field has been very well aware of this problem for at least the last 2 decades, and the perfusion technologies have been getting into clinical trials in many organs. I believe you've already been in Paul's lab, so you've seen the Transmedics heart pump already. This actually was more the first clinical trial that got the field excited actually happened in the lungs. They started using in Canada many more of the donor organs before they could use the pumps. And the liver trial that shows increased utilization just finished both in MGH and US as well as Europe that shows very significant increased utilization. So again, hopefully this is not too much of a reiteration of what you already know, but these perfusion systems basically mimic what the body does. To circulate the nutrients, you have a pump instead of a heart, you have an oxygenator instead of a lung. Most perfusion protocols use some analog to blood, which is typically a rich culture media, and it's supplemented by some kind of oxygen carrier. As far as I remember, all the clinical trials currently ongoing, these are red blood cells. And then there's some like additional stuff like tubing and kidneys, dialyzers for kidneys, etc. too. So we started doing machine perfusion actually when I came into the lab as a postdoc back in 2006. And the device looks a little bit like this. It was a normothermic system. We were using, just as I mentioned, the rich culture media, red blood cells as oxygen carriers, some plasma because we didn't have enough money to buy album. That's what we were using, and then a few other things. And it was kind of a mess. If I can show you the diagram, this is a dual circuit design. There's actually a second circuit that interacts through a dialyzer. The reservoir allows us to give some fresh nutrients to the organ and also is used as a sink for the byproducts of the liver. And this was a complete mess to run. I spent many hours in the lab banging my head against the wall to make it better. And I'll sort of basically run you through how we eventually got to a better system. So, but the first thing we wanted to see is if the system was actually good enough for anything. And our goal here was taking these DCD rat livers, 1 hour warm ischemic rats, and testing if our perfusion system made them better. At the time, the studies, they were at clinical stages, usually use pig systems. So we were, as far as I know, the first lab to try a rat system, which is much more cost effective, of course, to do the more crazy things you can do. But the key experiment is a DCD liver with machine perfusion treatment. The main controls are fresh controls, warm ischemic, no perfusion controls, and just perfusion controls. So this is also, I'll run through this very quickly, but basically if you take a 1 hour warm ischemic rat liver and transplant, there is no way it works unless you do machine perfusion, in which case you get over 90% success rate, which is same as what happens to a fresh liver or a normothermically perfused fresh liver. Anyway. So this showed like a binary change in the viability of the grafts. We could rescue these otherwise unusable livers and make them transplantable in the rat model. We didn't necessarily know what was going on though. The understanding in the field at the time was this was more of an immunological thing, partly because most transplant surgeons are also transplant immunologists by training. That's where the field's focus is. And the metabolism was not necessarily an area of focus. We wanted to see, to understand what's actually happening to the liver, because we only were doing this for 6 hours, and our suspicion was that it was much more faster metabolic changes. Especially the central energy metabolism was suspect in our eyes. So we use something called metabolic flux analysis. This is commonly used in biochemistry for like a metabolic engineering of bacteria and such. So this was one of the first examples it was done in the field of organ transplantation. So I'm not going to go through this detail. A lot of this is already published, and I'm happy to answer questions later on. Basically, what we do is write a mass balance on the liver, which allows us to basically just measure what's being secreted or uptaken by the liver, and then solve the mass balance and estimate what's happening intracellularly within the organ. So you basically get 2 for 1. You only measure the outflow fluxes, and you measure the intracellular fluxes, the reaction rates. So in this case, we are using HPLC, so we measure about 26 amino acids, and then we get another 20 plus measure estimates of the intracellular reactions this way, which is difficult to do unless you do labeled mass spec studies. So, oops, sorry, this is going a little fast. So we did that analysis. This is one of the metabolic flux analysis we do. It's comparing warm ischemic perfused livers compared to an in vivo rat liver that's fresh. And there are 3 basic findings here. One is we are rapidly running out of arginine, which is a nitric oxide donor, which is important for vascular relaxation after ischemic injury. So there was clearly some amino acid imbalance in the media we were using. The more obvious finding was we were not providing enough oxygen to these grafts, despite the fact that we have more than enough supply, both through the red blood cells and the oxygen we are giving them. There's clear lactate production, which is not good. It shows the liver is ischemic. And then if you look at the central energy metabolism fluxes, there is not enough activation the way we would expect to see. And the last part was that that was actually good news, was that we did have enough glutathione, etc. So the oxidative stress did not seem to be an issue, at least. So that was all good and well, but we were a little bit puzzled how to improve things, because we were giving the graft, the liver, all the oxygen we could potentially think of, and yet it wasn't enough of it. So I won't go through these details, but we actually connected these metabolic analysis to developing a predictor for the viability of the grafts as well. This is actually a fault detection algorithm borrowed from chemical process industries. And we use it to predict the viability of the graft, which again indicated that this analysis we are doing is actually predictive of the viability of the grafts too. So then we look at our system and said, okay, how can we make this better, at least for ourselves in the lab? Because running our normothermic system required essentially 3 people in the lab, keeping an eye on the system constantly. There's especially a liquid level control problem, because there are 2 circuits and you kind of have to keep balance between the 2 simultaneously, which usually means somebody sitting there and putting a dial back and forth for one of the pumps. So the idea at the end came to us was that, well, we have this liver, we put it at normothermic temperatures because that's what the situation it is in the body. But there is no law written on a slab of stone that says you shall do perfusion only at normothermic temperatures. So our idea was to take it down a notch and see if we can actually perfuse these grafts at room temperature, which will slow down the liver to about a quarter of the metabolic rate it usually operates at, which we thought was better for it to repair itself. There are multiple benefits to operating at room temperature, because suddenly the second circuit, which is necessary to provide all the nutrients, becomes not necessary. Which means we get rid of the second circuit. We actually don't need a heat exchanger anymore unless you want to do a regulatory just in case type of thing and your surgical suit is not temperature controlled. So we came up with this much more simpler device. The best part of this thing is one person can operate, and that one person doesn't even have to monitor the experiment the whole time. You can go have your lunch, come back, take your sample, and go back until the experiment ends. Because the demand of oxygen is actually so much lower at room temperature, we actually estimated that we can get rid of the red blood cells completely. So we moved from a much more complicated perfusion media to an asanguineous, basically off-the-shelf available media. And then I didn't get into the details, but we also estimated the time point we reach steady state from a liver perspective, and we thought 6 hours was not necessary. We could recover the graft within 3 hours. So we then tested that hypothesis that this simpler system is as good as the normothermic one. Again, the groups are the same, fresh or warm ischemic grafts, and now subnormothermically perfused 3 hours or not. And to make a long story short, this works just as well. Success rates are statistically identical. These are 5 out of 6 rats surviving after warm ischemia with perfusion rescue. And this is exactly the same results as we got with the normothermic grafts. And moreover, we looked at the ATP levels just to see if 3 hours was enough to recover. And as you see on the top right, it was more than enough to get there. We were actually exceeding the fresh livers a little bit. So we have cured everything in rats 3 times over. So the question is, well, that's great, but does this actually work for humans? So the next step was to scale up the system, and we do both pigs and humans these days. This was a study with research or donor organs. This is a collaboration with 2 good friends at the transplant unit, Jim and Heidi. So we receive these organs from New England Donor Services, our organ bank. Typically, they are DCD grafts, some kind of warm ischemia, plus there's usually a secondary concern too. So they are donated for transplant or research. If they're not accepted by any transplant unit, then they come to us for research or other labs. So there's a bit of a lag on my screen. I'm waiting. So we repeated the same metabolic, we repeated the metabolic analysis. At that point, we actually had more money. So we actually did a mass spectrometry analysis, which provides us not just 50 or 60, but actually about 200 plus metabolites. And for the most part, it confirmed what we previously had seen in the rat models. Again, the central energy metabolism was actually now getting much better activated during machine perfusion. The interesting note to us was that we kind of confirmed to ourselves that we are throwing away some good livers with the bad. There is that particular liver with 36 minutes of warm ischemia. 30 minutes is the cutoff clinically. But if you cluster these metabolic profiles, it clusters as a low warm ischemic time graft, which means it's actually much better than what you would think if you just looked at the population statistics and say everything about 30 minutes is bad. Clearly, this was a better liver than the other really bad livers. And we actually compared this is more recent, just published last year, compared normothermic and subnormothermic human livers side by side. So what we are seeing is that the subnormothermic livers actually have much lower arterial resistance, which is kind of a big deal because it's indicative of ischemic injury, essentially. This is one of the things that you look at when you're doing a clinical trial with a liver perfusion, that the resistance should be low and should remain low. So SNMP is definitely doing a better job. It also seems to be doing a much better job in terms of replenishing the ATP stores. As you can see, the numbers are much higher, whether you look at ATP itself or a normalized ratio, such as the energy charge. The drawback, however, it looks like we are not necessarily addressing the oxidative stress as well. The glutathione levels and acetylcysteine, etc., are much lower in our SNMP graphs. So probably the mitochondria are working really well at 20 degrees Celsius, but everything else is not fully functioning. So there's likely some ROS circulating around that is causing depletion of these antioxidants. So the ATP itself was an interesting story. So we did actually a small clinical trial to see if this is predictive of what happens to a graft. And again, I'll summarize very briefly. There's some more nuance to this, but basically what we saw was that the energy charge, which is a normalized version of ATP, normalized measure of ATP compared to ADP and AMP, is actually predictive of transplant early allograft dysfunction, which basically means within the first week after transplant, the liver is not working as well, which itself is indicative of long-term graft loss. Doesn't guarantee it, but is increases the odds very significantly. So this is actually an ongoing clinical trial at MGH. We are still collecting patient samples to increase the size and see if this can be used as a biomarker. So this is the metabolic engineering of the liver side. Now I'll move on to the cryobiology of the liver side. As I said, one of the issues is we can't use all the grafts because of our relatively poor preservation technology. The other problem is that we can't really preserve the organs for an extended duration. So as of now, for livers, our distribution circle is about 12 hours. And if you just do a back of the envelope calculation, if you can extend this to 3 days, you can basically distribute the organs, share the organs globally. It has multiple consequences. One is suddenly an emergency surgery becomes elective surgery, which means these things can be scheduled. This is a life quality change for transplant surgeons. If you've met Eric, he will tell you this better than I do. That also has significant cost consequences, of course. It makes everything cheaper for the system. It has the capability, at least, to increase utilization very significantly, because you can do better matches, and an organ that is not used in one area or one country or one continent can actually be used gainfully in another one, which has different constellations or a different patient. Because of better matches and less preservation injury, you actually need less immunosuppression. You lose fewer grafts to chronic rejection or acute rejection episodes, which means more of those grafts can actually be used for other people instead of retransplantation. And it actually unlocks a number of novel technologies, such as tolerance induction, which requires about 3 days to prepare the recipient. You need to deplete their immune system and then reconstitute with a combined bone marrow transplantation. As of now, this can only be done for living donor situations, which basically means kidneys. But for livers or vascular composite allografts, it can't be done practically, and 3 days will allow that. So it's a step change in terms of what we can do now versus what we could potentially do. So the first thing we tried was that, well, perfusion seems to work well enough. Can it actually just by itself extend the preservation? So we basically tacked it on to the end of static cold storage. So these livers are being preserved for 2 or 3 days with UW on regular ice. And then we are adding perfusion to the end, because the idea is that you will transport the organ regularly, but do an endpoint recovery using the perfusion system to get it back up and be transplantable. And that works reasonably well. We can actually extend it about 1 day. So in our hands, a 2-day cold stored rat liver is successful. It's successful transplantable with 50%. This is 3 out of 6 animals surviving. If you perfuse, the success percentage goes to 100%. But for 3 days, we couldn't do anything. Whether you perfuse or not, those grafts were not surviving. And although 3 days is kind of an arbitrary line in the sand, we wanted to make a significant difference so that this is worth the effort of adding technology to regular, very simple cold storage. So that's where we went to a little bit back and look at, what we can do. So hypothermia, ice cold storage is the gold standard clinically, as I mentioned. Perfusion is where the field is going now. What we asked ourselves was that, well, can we improve on that static cold storage period in between where you can actually transport the organ? Now, there are multiple approaches there. John is working on vitrified organs, as you know well, and that promises storage of multiple years. But we want to start with something much more gentler and easier, which is why we went to supercooling, which doesn't involve any phase change. You are just reducing your temperature about 10 degrees, which at least theoretically reduces your metabolic rate of the graft during storage by about half. It reduces to about half, which again means that you should be able to improve duration by twofold. So this is not completely crazy. You may have seen these slides before, but this is done this kind of stuff is done, this exploiting of the high sub-zero, 0 degrees to minus 30 degrees Celsius range is very commonly done in the nature. The frog, which can freeze and thaw itself successfully, is the poster child. But there are also mammals who do this trick on a regular basis. So these are the Arctic ground squirrels, and I believe their habitat extends to northern parts of Minnesota, Wisconsin, and Michigan too. So these little critters can actually supercool. They can survive in exterior temperatures of minus 30 degrees Celsius. Their core body temperatures goes down to about minus 8 degrees, and they can basically supercool with an intermittent rewarming up to 3 weeks. And they're not the only ones who can do this trick of supercooling. There's a crocodile that can actually pull off the same trick to preserve itself. So clearly nature exploits this temperature, but in cryobiology, we weren't necessarily exploiting it that much. So that's what we wanted to investigate. So that wasn't necessarily easy, and we failed a bunch of times. I'll just summarize here what worked. So obviously perfusion was an important part because that's what we wanted to use to infuse the grafts and prepare them and also recover them from cold storage. Obviously, we want to use lower temperatures, and we did some stability analysis and found that minus 5 degrees plus minus 1 works. And then we added some intracellular protectives and extracellular protectives to mimic what the nature and organisms in nature do. Oops. Yeah, sorry, the slides are a little bit unresponsive. So we use multiple things, PEG especially, but the most critical one is 3-OMG. It's a glucose derivative that looks enough like glucose that it can go through the GLUT transporters into the cells, but because of the extra metal group cannot be broken down, which means the intracellular carbohydrate levels go up very significantly. And this is exactly the trick that the frogs and the other organisms pull too. So the protocol we came up with, this is with Mesh and Mehmet, is to first do an initial perfusion to low 3-OMG, then flush with PEG added UW, keep it in the supercooling temperatures for 4 days, and then recover with machine perfusion and transplant. So to rehash, if you can actually do this successfully for 1 day easily with rats. 2 days success goes to 50%, 3 days or more, it doesn't work. With supercooling, it actually works perfectly for 3 days. The survival in our hands is 100%. And for 4 days, the success goes to about 58%. So there's clearly a limit to a few days, but clearly we are also increasing the total storage duration very significantly. And I'll briefly summarize a little bit of what's happening. We actually tested specifically which components of this protocol are important, and it turns out everything is important. You can't take out supercooling or perfusion and expect it to work. Everything does unless you do all 3 things. I'll go through this very slightly because it will be relevant with the human livers. If you compare the 4-day supercooled livers, which ones survive and which ones don't, there are 3 major differences. One is the resistance increases quickly and stays high throughout. As I said, it's a common indicator of ongoing ischemic injury. In correlation, oxygen uptake is lower in the non-surviving grafts. Similarly, bile flow, which is an important marker of cholangiocyte function and liver in general, is lower in non-survivors. And if you compare the supercooled livers versus cold stored controls, the ATP levels are very significantly different as well. Now, if you actually take this rat protocol and try it with human livers, it freezes. This is what Rainier is showing with a human liver. So we had to re-engineer that protocol. This is with Shannon, who's also faculty at CEMS now, and Rainier, who's now back in Netherlands in the clinic. So we had to re-engineer that protocol quite a bit. We needed more cryoprotective agents, glycerol and trehalose, to keep the livers actually supercooled. And then we needed to add a hypothermic perfusion step at the beginning, at the end of supercooling. The first one is so that these protectants are diffused across the entire organ. The human liver is about 2 kilograms. The rat liver is about 15 grams. So the flush wasn't cutting it, and we could see the freezing on the periphery. And then you need to remove the protectants gently, because otherwise they can cause some injury. So the experimental design is a little bit tricky because these are donor research quality human livers. They come to the lab with about 15 hours of cold ischemia already. So we put them on the pump for 3 hours. We load them with ThermoMG, but we also analyze their state. So that's our baseline, the state where they came into the lab. And then we flush them with UW plus additives, supercool them for 20 hours, and then a perfusion recovery, which is our post. So that is after supercooling. In clinical trial terminology, we are basically doing a non-inferiority trial. Whether the supercooling actually does change anything is what we are looking at. So once the screen refreshes, I don't know you guys, but mine is a little bit lagging. So we compared this pre and post, and these are the same indicators I mentioned in the rats. If you look at energy charge, basically there's no difference. They increase over perfusion significantly, and that increases the same before or after supercooling. Bile production is the same before or after supercooling, which is actually kind of impressive because you run out of bile salts. There is no liver enzymes. The LFTs are stable and at lower levels. There's no major increase there. And then the resistances are low and stay low. And again, there's no difference before or after supercooling. And then we did a simulated transplantation. This is, since we can't do an actual clinical transplantation, this is a simulated one with 2 hours oxygenated perfusion with reconstituted blood. And this essentially shows the same thing, that this is a stable graph. The energy charge is staying constant. Bile production is ongoing. ALT and AST stay low, which is impressive because it means there's no cellular damage period. Resistances stay low. And lactate is actually starting to go down. Lactate is not perfect, like Tim Pruitt was telling me. But these are at this point 47-hour stored human livers that were rejected for transplantation for multiple reasons already. So this is actually pretty good given the organs we are working with. So I'll summarize there, and of course I'll be happy to have questions. First thing is perfusion is a very important platform technology because you are able to preserve the organ in a functional state as opposed to a static state. Which means you can assess what's going on, but you can also prepare the organ for whatever you want to do, such as loading of the protective agents. And it also allows you to repair the organ on the pump, as we clearly see with these both warm and cold ischemic graphs. Actually, it allows you to potentially deliver pathology-specific treatments. For instance, we could treat fatty livers. There's a whole other research ongoing to get rid of fat in fatty livers. You could even do genetic modifications or introduction of cell therapies and that sort of thing, which are again ongoing projects that we are just starting. I talked a little bit about assessment, but you actually can do this in many different ways, and we are just looking at transcriptomics right now. And then the other point I want to make is this is a constellation technology, as they call it. It's not just one thing. This life is not simple in the biomedical engineering world anymore. You can't just invent insulin to treat a disease. You need multiple things working. But if you actually put the time and effort to develop such a technology, then you can actually still break some world records, as we have shown. So with that, there's a long list of people I need to thank to. I won't name them one by one, but it's their work that I'm really presenting, and it's thanks to them these things work. And of course, I acknowledge our funders who make this work possible. And that's it for me. Thank you.
Thank you, Korkut. So very exciting talk, and I have tons of questions, but I know Korkut, and I can call him up anytime. So why don't we open the floor to questions?
Just a quick question about the asanguinous media. Sorry, could you reiterate what that was and why it's able to replace blood without causing any serious problems?
So the media is, I'll try to go back quickly, is essentially the same with the exception of red blood cells and plasma. The media itself is Williams media E, which is a hepatocyte culture medium. It's commonly used in admetox type of studies. We use them for cell cultures. It has a lot of things, not just a buffer, but nutrients, vitamins, etc. Red blood cells is the main thing we drew. Plasma we were using as a source of albumin, but it's something you had to isolate fresh. Same thing with red blood cells, so we no longer needed to do that. Hydrocortisone is an immune suppressant, which is actually something we patented. But it suppresses the Kupffer cells, at least that's our hypothesis of what it does. So the liver does not react to whatever you're doing to it. And insulin and pan-strip are standard things. So we are not really changing anything. So asanguinous doesn't really change the media itself too much. The difference is because we are operating at a much lower metabolic rate, we don't need to provide as much oxygen to the graft. We can just get away with hyperoxygenating a little bit, going above the usual dissolved oxygen levels. But we don't need to provide the red blood cells. And again, as the transplant result shows, that's good enough for the liver.
Thank you.
Thanks, Korkut.
Sure.
Other questions, Casey?
Yes, so do you still use oxygenation at sub-zero perfusion?
So we don't do perfusion sub-zero. There's an argument to be made that you could still add an oxygen carrier into the media during that time, and that may actually improve things. It will be static because at sub-zero, unless you are doing it at equilibrium state, you could actually initiate freezing by perfusing it at supercooled temperatures. Actually, you will do it if you perfuse. But yeah, there's definitely an idea to add some oxygen carrier to the culture, the preservation media. The thing is, that kind of thing has been tried before. Just there's a long list of things added to UW, and they tend to improve things so slightly that they never made it to the clinic. Oxygen carriers, antioxidants, apoptosis inhibitors as an additive to UW have been tried for the last 40 years. And at least as far as I know, none of them have made it to the clinic. We still use the traditional UW developed back in the 1970s. So I suspect its effect will not necessarily be significant. But yes, that's definitely something that can be tried.
Okay, and just to follow up, is there a trade-off at all? Like, would oxygenation cause more reactive oxygen species or something like that? Or would it only just have like a slight benefit?
Sorry, could you repeat that? I couldn't hear the first part.
Is there a trade-off? Like if there's more oxygen, do you get reactive oxygen species, or is there a downside? Right?
Yeah, is there any
No, yeah, that's exactly, I think the balance you need to strike. Early on, these are damaged tissues, probably not properly functioning mitochondria. If you make them work, there is more ROS being produced, certainly. How damaging that is for transplant purposes is a whole other question. My suspicion is it's not that critical. I'm sure there's a threshold beyond which you damage things too much, but yeah.
Thanks.
So basically, you haven't explored that edge yet. Is that right, Korkut?
That is true. We haven't explored it much.
Okay. Great. Other questions? Soren?
Are you guys able to sort of monitor, like, I guess specifically for the human liver, which is a lot bigger, to make sure like whatever you're perfusing in is actually reaching all the cells in there, or like all parts of the liver, rather than like sort of this bulk measurement of like the whole liver is kind of doing well.
Do you see any regional differences, Korkut, or perfusion maybe not getting to all parts of the liver, things like that?
So you can actually visually detect it fairly easily. If you're not oxygenating, it quickly turns dark. And in some of the rat pictures there, that was actually there. This typically happens around the periphery. The central area is usually well perfused because that's where the catheter goes in. But the periphery immediately starts to turn black. And if you don't oxygenate it well, it will turn really like black dead tissue. So visually, it's relatively easy to guess. That doesn't mean we necessarily know where, say, the protectants like 3-mg are going, but their concentration is within the human tissue. Clearly, there's more room to be done, and some kind of imaging technique could be very useful. But in terms of overall perfusion quality, that's easy to just visually detect.
So Sarin works with Mike Garwood, who's the associate director of our Center for Magnetic Resonance Research. So you may be getting a call, Korkut.
That will be great.
Other questions? Yes, Basu. Oh, well, why don't you go ahead, Matt, and then Basu.
What are the considerations for transporting in a supercooled state to within like the US or possibly like outside?
So the chiller we use is a gigantic thing that was manufactured in Michigan specifically for us. But in terms of actually what we need to do, the heat load is not that much. And we have much more portable chillers that could probably be made to work this. You need to develop a custom device, of course, just for this purposes. But at least to my engineering sensibility, it's not that big a deal. In terms of like logistics, etc., I'm not very concerned because some of the perfusion trials already ongoing involve transporting the entire perfusion device between centers too. And you basically just have like some like wheels, etc., so that you can cart it off, and then you put it on the plane, and that seems to work reasonably well enough. So, you know, it will be a relatively larger thing than the icebox, of course, but it does not seem like a major challenge for you just need to put some money into it and develop that system. It does not seem like a technical challenge.
So just a quick follow-up on that, Korkut. So you are thinking of transporting in the supercooled state, not perfused, right?
Yes, in general, yes, that's our thinking.
Okay. Great. Basu.
So I remember reading about a hypothermic recovery after CPA unloading. So how effective or how important is that stage before, like, let's say subnormal thermic or normal thermic perfusion? And is there any difference if you directly bring it up to normal thermic perfusion after CPA unloading? In terms of recovery?
Yeah, so we, let me see if I can go to that quickly. You are talking about step 6, right? The hypothermic perfusion after supercooling.
Yeah.
So that was critically necessary to get it to work for human livers. Part of the reason is you want to get rid of these CPAs very quickly, but you also want to do it gently. With the flush, we clearly weren't doing it well enough. You can just like flush it with a giant syringe or just do a gravity controlled, run the UW through, but it looks like the pressure was not enough. So with a pump, even though the flow rate was low, it worked much better, both to introduce and remove. You can just put them up to subnormothermic or normothermic temperatures because some of those protective agents are actually toxic at higher temperatures, like even PEG itself is not good. So you need to remove them before you actually kind of activate the metabolism of the liver. In fact, I won't talk about partial freezing today, but I think it's in your coursework a few weeks after me. That step, both introduction and removal, have multiple steps, and we are finding that that's very important to do. And actually, Greg Fahey has a lot of work with vitrifying kidneys too, which also shows that there's a very fine balance in loading your CPAs at the right amount, at the right velocity or flow rates, so that it doesn't damage. Our hypothesis is that if you don't do it the right way, the endothelial lining is being sheared, and that causes long-term injury. But we haven't really explored that in as much detail as I would like yet.
What's the total molarity, Korkut, when you get down to -4 in the perfusate? Since you're talking about pulling out the CPA, I'm just wondering what the total molarity is.
I don't remember off the top of my head, but we generally try to stay not too much above 0.3 molars, so that we are not making anything major, causing any major, dehydration.
But this would be 0.3 above physiological?
No, it will be about 0.4 or so. 0.3 to 0.4 is usually where we double. I don't remember in the liver case. In the rat case, it was, I think, 0.30, 32, I want to say, but I could be lying. I'll need to go back and check.
Okay. What he's not telling you is that he turned this liver into a frog liver, right? Korkut?
Yes.
And he's loaded it with a non-metabolizable glucose. You didn't get into that part, right?
I mentioned the TRMG a little bit, but yes, I didn't get too much into partial freezing are where we go, and dehydration is a completely different thing that I haven't dabbled much in yet.
Okay. Yeah.
Quick follow-up. My question was, after the CPA unloading, if there was like a hypothermic recovery stage, because I remember reading about it, but maybe not. Because here it's just removing the CPA and then directly to subnormal thermic.
So there is no hypothermic recovery. Sorry if I missed that question. After removal, this is a 10-minute short unloading. There is no hypothermic recovery stage that we use. We go to subnormothermic directly. Now, that being said, we do have some gradual rewarming. There's one paper that's just being submitted. We tried it for kidneys, and it seems to work better. So the idea there is, instead of doing the stepwise, just starting at around plus 5 degrees or so, and gradually increasing temperature all the way up to 37 degrees and get the liver ready for transplantation. And there's some data. There's actually a clinical trial done in the Netherlands that shows this is actually more gentle on the liver, and it actually seems to work better. But at least I haven't seen a more detailed metabolomic analysis of that yet. I assume that is true, but I don't know for sure yet.